Hello, good afternoon, everyone. My name is Maher Bakr Qasim. I'm your professor for Physics 1300. I will be continuing with you with the remaining of the lectures for this course. We will continue exactly the same as Matt started it. So we will be having pre-recorded lectures so you can watch. And then during the lecture times, we will be having Zoom sessions to answer your questions and solve some of the questions that you would like to be solved. So we will start today with a new topic from chapter 7. So let's get started. Okay, so in this lecture, we will cover the work done by constant force and the kinetic energy and the work energy theorem. And then we will end with the work done by the gravity. So what is work? In general, we know that work is an effort that is exerted. And in this course, in our physics here, we know that the work is defined as the force that has been exerted on an object that resulted into a move for that object. Now, also remember that the force could not be perpendicular on the displacement vector, as this is going to result into a zero work. So let's look at this person who is pushing a lawnmower. We can see that the force that he is exerting on this lawnmower is F, and this resulted into a displacement, as you can see here, delta R vector. This means that this force has done work. How much is this work? This work is given as W equals to the force magnitude times the magnitude of the displacement times the cosine times cosine theta. This is the result of the dot product between those two vectors. So in general, W equals to, mathematically, it's F dot those two vectors. Now the result is scalar. The dot product in general will give me, of two vectors, will give me a scalar. So the dot product here resulted into this magnitude of the first one times the magnitude of the second one times cosine theta in between. So this is the expression that we have seen. Let's look at this expression further in more details. Now, if I have this sofa that's being pushed using this force, as you can see, the displacement vector will be along this surface. Then, if I am to calculate the work, then the work would be the magnitude of the first times the magnitude of the second times cosine the angle in between. So here, the angle in between is theta, then W equals to F delta R cosine theta. In general, if I am to look at the components of those vectors in general in a coordinate, a standard coordinate. I can look also at the components of the force and the components of the displacement. So the work done would be the component Fx times delta x, component of the displacement on the x-axis, Fy times delta y. How? So let me go to slide 6 first. Then by calculating or obtaining those components, if I look at the force F here, it can be projected, as you can see, on the x-axis as Fx, on the y-axis as Fy. This displacement vector delta r is delta x on the x-axis and delta y on the x-axis. So I can calculate the work by using the components projected on the coordinates for the force and for the displacement vector. Now, another way I can look at it, if I put my coordinates such that x is along the displacement vector, what did I do? This means that this displacement vector doesn't have a projection on this y, because now this displacement vector, delta r here, is along the x-axis and perpendicular on the y. So in this case, what did I do? I eliminated the second component for the displacement. In this case, the only component that is going to contribute to the work is the x component of the vector. Why? Because my y component now of the force, because now my y component of the force is perpendicular on the displacement. In this case, the work done by Fy will be 0. So only as a result, as you can see here, only the component that is along the displacement is going to contribute to the work. The component that is perpendicular on the displacement is going to contribute a zero to the work. Now, if I look here at W equals to F delta R cosine theta in general, I know that for the vector Fy, if I look at this vector by itself, theta here is 90 degrees. So the Fy and the displacement will have a 90 degrees, which means 0. That's why my only component in this case that's going to contribute is the component that is along the displacement. Let's look at a few examples. If you are pushing a 9-kilogram lawnmower with a constant force of 14 Newton across the flat lawn, the lawnmower handle makes an angle of 25 degrees to the vertical neglect the friction. If you do 27 joules of work on the lawn mower, what is the resulting displacement? B, what is the work done by the normal force on the lawnmower? So, what do we have here? We have 9-kilogram lawnmower and a constant force 14 Newton across the flat lawn. The lawnmower handle makes an angle of 25 degrees to the vertical. This is the angle. Neglect the friction. If you do 27, so we have here the work. The work is given to me as 27 joules. The angle to the vertical is also given to me. The mass is given to me, 9 kilograms. We need to calculate the displacement. So in this case, as you saw, if I am to look at this lawnmower as this point, and then assume that the displacement delta R is in this direction, the force in this direction, which is 14 Newton. So if the angle here is 25 degrees, and the angle here is 65 degrees. So, as I said, the only force that's going to contribute is the force that is along the displacement, which means if I am to take if I am to look here, this is x, this is y, only the x component of the force is going to contribute to the work, right? Which means, or I can apply the F delta R cosine theta. Now, if you think about it, this F with the cosine theta is indeed the Fx, right? Isn't this F? When I project this F right on here, this will be this F cosine 65. This one is Fx. However, if I apply this equation right away, it's been already taken care of by putting the 27 equals to 14. I need delta R times cosine 65 degrees. This means delta R equals to 4.6 meters. So now we know where did this cosine theta come from. Where did it come from? It came from the projection of this force right on the direction of the displacement, because this is the one that's going to contribute to the work. The other component that is perpendicular on the displacement is not going to contribute to the work. Now, what is the work done by the normal force on the lawnmower? The normal force is perpendicular. If you think about it, if this is the again, if this is the lawnmower that we talked about, represented by this dot, then this is the gravitational force, Ft. This is the F, Fn, right? In this case, since the normal force is perpendicular on the displacement vector, then the work done is zero. So let's look at a second example, where in this example we have a mug with a mass of 0.5 kilograms slides along a flat horizontal surface for a distance of 1 meter. 1 meter. Slowing down due to friction as it slides. What is the work done by the gravity on the mug? Again, we said in this case, the gravitational force will be perpendicular on the displacement vector. This is going to result into a 90 degrees, and that's why W equals to Fg delta R cosine theta, theta 90 degrees, 0, W is 0. A third example, same mug, it has a weight of 0.5 kilograms, slides along a flat horizontal surface for a distance of 1 millimeter, slowing down due to a friction as it slides. What is the work done by friction on the mud? Assume that the gravity G equals to 10 meter per second squared for simplicity. Now, in this case, we have mud that slides in this direction, delta R. However, the friction is in this direction. We have Fg, we have Fn. Now let's see what is given to me. We want to calculate the work that has been done by the friction force here. So I have W equals to F at magnitude times delta R times cosine theta. Now notice that the theta between FF and delta R is 180 degrees. So cosine theta is -1. Okay. Now, if we go back to see that the work done by the friction on the mud, the friction coefficient, the static friction coefficient is not given to me. So in this case, the best answer to this problem would be D. Not enough information provided because the mu s is unknown. But this is how we solve it in general. You can calculate the F due to the friction, then you can calculate the work done by this force. Let's look at this example. In this example, we have a bicycle that is slowing down on a flat stretch of road due to a constant frictional force of 43 Newton. Now the frictional force has been given to me. If your total displacement is 210 meter west, this is the displacement vector. Before coming to a stop, what is the work done by friction in your bike over this distance? Again, I can look at this problem. This is delta R. This is F friction, F normal, Fg, all are contributing zero to the work. So in this case, if I am to apply the expression W equals to F times delta R times cosine theta, and we know here theta is 180 degrees, so cosine theta is -1. Then W, if I take this direction as the positive direction, the west, then again 43 times 210, and work will be this one. Work will be minus 9 to the power 3 joules. Now let's look at kinetic energy. As we know, any object that is facing forces will result into an acceleration on that object, and this is going to result into a velocity. This velocity basically, will, as long as the force is there, will change, and this is going to result into a change into the kinetic energy. So if I look at the total work, this total work will result into a net force, and this net force is going to result into a kinetic energy. Why? Because this force is going to induce acceleration. This acceleration is going to induce velocity and so on. So I will end up with a kinetic energy due to a very specific velocity. I can calculate the total work that has been done on this object since the force has been applied on that object. So if the force has been applied at t equal 0, then this is going to be my initial velocity. I calculate the kinetic energy at, and then this force has been applied till it was removed. Last moment it was removed. The velocity was Vf, for example, which is the final. This is going to result into a final kinetic energy. So at the end, the total work will be the difference between both kinetic energy. So W total will be half mv squared. Again, v is the final speed minus half mv naught squared, where v naught is my initial speed. So I can calculate now the total work that has been done by this force by calculating or knowing the difference in the kinetic energy between the final state and the initial state. Again, The kinetic energy is given as a unit of joules, and as I said, the total work is the difference between the final kinetic energy minus the initial kinetic energy. The symbol for the kinetic energy is EK. Then we can say that the total work that has been done on an object equals to the difference in the kinetic energy between the final and the initial, where the force was applied in that object. So if the kinetic energy is increasing, then definitely this means that the velocity or the speed is increasing. As if the kinetic energy is decreasing, this means that the speed is decreasing. So let's look at this example where we have an ice skater of mass 55.2 kilograms falls and slides along the ice, undergoing an horizontal displacement of magnitude 4.18 meter before stopping. So this is my displacement, the magnitude of my displacement vector. The coefficient of kinetic friction is 0.27. So this is my mu s. What is the work that has been done? The work, what is the work done by friction as a skater slides? So here we have the mass, we have Fn, Fg, we have Ff, and then this is delta R, we have the mu s as 0.27. What is the work done by the friction? So here we calculate the Fn. Fn equals to Fg, then Fn is mg, 55.2 kilograms times 9.8. Fn equals to 541 Newton. Then F is mu s times Fn times 0.27, 146 Newton. Now, the work is Ff times delta R times cosine theta. We know that cosine theta is 180 degrees, then this means cosine theta is minus 1, 146 times 4.18 is minus 610. 0.5 joules. So this is the work that has been done due to the frictional force. What is the skater's initial kinetic energy? The skater when we need to we know that the skater has reached a stop after sliding for 418. So W equals to delta K, or W equals to EKF minus EKI. We know that V, so W equals to half M V squared minus half M, this is this one, F I squared. He reached to a stop, which means the final velocity was, speed was 0. This means the work equals to minus half 55.2. I know that the work is minus 610.5 equals to minus half 55.2 VI squared. This means VI squared equals to 2 times 610.5 divided by 55.2. VI squared is 22.2, and VI equals to 4.7 meters per second. What is the skater initial? Oh, we did the initial speed. What is the skater initial kinetic energy? Okay, so we did both of them. Kinetic energy, we go back to here. So this is the initial speed. The skater's initial kinetic energy is half m VI squared, which is basically equals to joules. Right from here, this is EKI, this is 0, so W equals minus EKI, W is minus 610, so EKI is 610.5 joules. Okay, so Let's look at example uses the work energy theorem. We we've seen in the work energy theorem that the energy will be transferred from one form to another, it cannot be destroyed or created. And that's why we have seen that the work that has been done is transformed into a change into the kinetic energy. So let's look at this example. In this example, we want to calculate, as we will see later on here, the speed of the wagon after being moved 0.75 meter. So a girl pulls a wagon load of toys with mass of 20.8 kilogram across a horizontal ground. She is exerting a force on the wagon of 95.6 Newton, inclined at 35 degrees above the horizontal. So I'm trying to look at it this way. This is, the force. That's Q. That's M. And this is 35 degrees. The kinetic friction force on the wagon has magnitude of 75.5 in Newton. Use the work energy theorem to determine the speed of the wagon after being moved 0.75 meter, assuming it starts from rest. Okay, so what do we know? We know, let me write those ones. Mass, 20.8 kilogram. Force, 95.6 Newton. Theta is 35 degrees. The friction force is 75.5 Newton. Use the work energy theorem to determine the speed of the wagon after being moved 0.75 meter. Okay, so let's move. Okay, so we'll redraw five and here. Okay. So I have N 20.8 kilogram. That is 75.5 Newton. Delta R times 75 meter. And that equals to 95.6 Newton. Okay, so if we use the energy theorem, we have W equals to half M V M squared minus half M V I squared. So in this case, we know that for W, we look at the work that has been done by the net force or by the contribution of those forces. We know that Fg and Fn are perpendicular and not going to contribute. The only forces that will contribute is Ff that has an angle of 180 degrees, and we have in between the displacement and the friction force, and also we have the F that has an angle of 35. So if I am now to write the the total work due to the F and due to the FF, it will be F delta R cosine 35 degrees. This one is minus FF delta R, and this equals to half m v final squared minus half m v initial squared. We know that the wagon starts from rest, which means that vi is 0. So I need here to substitute and solve for the velocity. So I have F as 95.6 times 0.75 times cosine 35 point 2 minus 75.5 times 0.75 just to have times 20.8 VF squared. This means if you do calculation here, this is going to be 2.11 equals to 20.8 VF squared. Then F squared equals to 2 times 11 divided by 20.8. F equals 2.45 meter per second. So this is the speed of the wagon after 0.75 meter. Okay, so the last example in this lecture will be the work done by the gravity. In this case, we have an apple that has fallen from rest with a mass of 110 grams for a distance of 5 meters. What is the final speed of the apple just as it hits the ground? So again, we can use the work energy theorem. So in this case, If I say W equals to half m squared f minus half m squared I, starting from rest, which means the speed was 0, then I know the work due to the gravitational force would be uh, delta R. If I take this one as the positive, and then I know that this is Fg, positive going downward, then delta R would be 5 meter. I have here Fg is delta R equals to half m AF squared, and Fg is mg delta R equals to half m squared, and cancel, and V f will be equal to, how much is V? 9.9 meter per second. Okay, so this concludes this lecture. I'll see you in the next lecture.